Okay, great. I think we can get started. So our second talk for this morning is on singular Hodge theory for combinatorial geometries by Jacob Methern from the University of Bonn. Over to you, Jacob.
Yeah, thanks, Pranav. So I'm happy to be here. If you have questions, I guess there's a way to ask them. So I'm happy to answer them, though, or try to.
Yeah, so the in-person participants can, they have mics, so they can just speak up and you'll hear them.
Okay.
And the online participants can type their questions in the chat box or ask to be unmuted. You can raise your hand and...
Right. I've seen people use the raise hand feature. It's good.
Yeah.
Yep. Okay, so
Thank you.
yeah, so I've been enjoying this conference so far. I've seen some talks that are related to the kinds of things I'll talk about today, which is good. So, okay, let me just start. So the topic of my talk is singular Hodge theory for combinatorial geometries. So that's a lot of words, but so it's based on two papers that are on the archive. So the main paper it's based on is this one, which I've highlighted, and this paper is a smaller paper that kind of it develops the background results that we need for this one. So this is joint work with Tom Braden, who's at UMass, June Huz, who's in Princeton, Nick Proudfoot, who's at Oregon, and Botong Wong, who's at Wisconsin-Madison. Okay, so what I want to do is I want to tell you about two problems involving hyperplane arrangements. So you've seen lots of talks, or a few talks about matroids already. So hyperplane arrangements are sort of the realizable matroids, or some people call these representable matroids in the previous talks. But of course, not every matroid comes from a hyperplane arrangement. So the sort of idea in my talk is I'll tell you about two problems that make sense for arbitrary matroids, but you have some extra structure when they're realizable. And these two problems are going to be called one's going to be called the top-heavy conjecture, and one's going to be called. So I'm going to associate something called Kajan-Lusztig polynomials to these matroids or hyperplane arrangements, and these polynomials I'm going to show that they have non-negative coefficients. Okay, so both of these problems make sense, as I said, for hyperplane arrangements and arbitrary matroids. And in the case for hyperplane arrangements, these things were both already proven by other authors. And I'll talk about their proofs because they use geometry. And in the case when I don't have a realizable matroid, the problem still makes sense, but I don't have geometry, but I'm going to try to simulate that geometry. And this is what our contribution was. So this is what I'll talk about in the last part, sort of these two problems for all matroids. And in the part in between, part 3 here, I'm going to introduce these Kajan-Lusztig polynomials. And if you've heard the term Kajan-Lusztig polynomial before, it has to do with Coxeter groups or flag varieties or Schubert varieties, these kinds of things, Hecke algebras. These are not the Kajan-Lusztig polynomials I'm going to talk about today. I'm going to talk about sort of a theory of Kajan-Lusztig polynomials for matroids that's analogous in some sense, but the two theories are different. They just share a lot of similar properties with the classical ones. So I'll talk more about this in section 3. Okay, so that was some kind of overview. Let me get started. Everybody can see the screen? It's okay? Yeah?
Folks at the back, can you see the screen clearly? Great, everyone's nodding, so I guess.
Okay, great. So let's start telling you about these two problems. So V is a vector space. I don't really care about the field, but you can work over the complex numbers. This is easiest. So A is going to be a finite set of hyperplanes. So this is codimension 1 subspaces inside this vector space V with the property that if I intersect all of the hyperplanes inside of this collection, I get the origin. Okay, so here's a definition. A flat is what I'm going to call the subspace, any subspace that I get by intersecting some of these hyperplanes. So it's any subspace obtained by intersecting some hyperplanes. So I'll show an example here. Okay, so here's the first example. So I take my vector space, this is sort of a cartoon picture. I take it to be C2. Okay, so I have some two-dimensional space, or R2. Okay, and then I have three hyperplanes. Here's the first one, hyperplane 1. I have hyperplane 2. And I have hyperplane 3. And they have the property that the intersection of all of them is the origin. Okay. So now what I would like to do is I would like to encode some combinatorial data about this hyperplane arrangement and all of these flats, these intersections I get. So there's this thing called the lattice of flats. Okay, so I'm going to write it as L sub A, or L of A. So, okay, which subspaces can I get by intersecting hyperplanes? So if I intersect none of the hyperplanes, I have the vector space V that I started with. If I intersect any one of the hyperplanes with itself, I have the hyperplane itself.
Jacob, there's a question. Oh, I think this may be from the previous talk. I'm sorry.
Okay,
no
no problem.
Go ahead.
Yep, okay. So now if I intersect two of the hyperplanes, so like H1 and H2, I get the origin. And if I intersect three of the hyperplanes, I still get the origin. So the only new subspace I can get is the origin. Okay, so I've written down all the subspaces I can get by intersecting hyperplanes. And now this has the structure of a poset, and it's ordered by reverse inclusion. So this origin is contained inside of each of these lines, and each of these lines is contained inside of the vector space. Okay, and it's a ranked poset. So let me move this a little bit. So it's a ranked poset, and it's ranked by codimension. Okay, so this is a codimension 2 subspace, this is a codimension 1 subspace, this is a codimension 0 subspace. And I'm going to call the elements at these particular levels inside the poset, at these particular ranks, I'm going to call them by L with a superscript for that rank. So these are all the guys at rank 1 and so on. Okay, so the first problem is called this top-heavy conjecture. So this top-heavy conjecture says that if I start with a hyperplane arrangement and I build this poset like this, then this poset should have a certain shape. It should be top-heavy. But this poset is so symmetric, there's really not much to see here. Okay, so let me do one more example that's slightly more complicated so that I can explain to you what this top-heavy conjecture says. Okay, so now I want to do the next sort of example up in this family. So here I had 3 hyperplanes, codimension 1 subspaces inside of a 2-dimensional vector space. Now I'm going to have 4 hyperplanes inside of a 3-dimensional vector space. So instead of 3 lines inside of R2, I'll have 4 planes inside of R3. Okay, and again, they should be generic, but they intersect. The intersection of all of them is the origin. So I'm not going to draw this picture for you, but I'll instead draw the lattice, or copy paste the lattice. Okay, so let me explain to you what this means. So here's the 3-dimensional vector space I start with. I have 4 planes. And then when I intersect 2 of the planes, H1 and H2, I denote that by H12. So this is the line I get by intersecting the plane H1 and H2. Okay, so in that way, by intersecting these pairs of planes, I get 6 lines. And then if I intersect 3 of these planes, I again get the origin. And intersecting 4 of the planes gets the origin again. Again, this is a very special case, right? My planes are generic and their intersection is the origin. Okay, so now I can explain what this top-heavy conjecture says. So it says I should draw a horizontal line through the middle of the poset, like this, okay? And it says I should start comparing the number of flats, the number of elements on complementary ranks. And sort of on the top, there should be more elements than on the bottom. So let me say precisely what I mean. So if I compare the number of elements here to the number of elements here, on the top, I have 1 element, on the bottom I have 1 element. So I have 1 is greater than or equal to 1. So this one is the top, and this one is the bottom. Okay, and then let's now go 1 level down. Let's compare this one to this one. So here I have 6 is bigger than or equal to 4. Okay, so as I start comparing complementary ranks, the thing on the top should be bigger than or equal to the thing on the bottom. This is what the top-heavy conjecture says. And I keep doing this until I hit this horizontal line in the middle. So let me write this down precisely. So this is something called the top-heavy conjecture. And it was a conjecture due to Dowling and Wilson in 1974. So it says, for every k less than or equal to 1/2 the dimension of the vector space that I started with. So this means I'm drawing this 1/2 the dimension of the vector space is this horizontal line, this orange line. The number of elements of rank k is less than or equal to the number of elements of co-rank k. Okay, so this is exactly what I described to you. All right. So this is not a conjecture anymore. So Dowling and Wilson conjectured this not just for hyperplane arrangements like I'm explaining here, but for arbitrary matroids. Okay, so a matroid has one of these posets associated to it. So equivalent data of defining a matroid would be giving this lattice of flats of the matroid. So you could give a matroid by giving a poset satisfying some axioms, but it doesn't have to come from a hyperplane arrangement. So still you can ask whether this poset is top-heavy. Okay, and that's what Dowling and Wilson asked. But in the case of hyperplane arrangements or realizable matroids, Junhe and Botong Wang proved this in 2017. So 43 years after the conjecture was given. And I'm going to explain some ideas of their proof in the next section. And then what we did is extend this to arbitrary matroids. And you have no geometry here. So He and Wang's proof relies a lot on geometry, but we don't have it, but we have to sort of emulate it. Okay, so good. Everybody understand this conjecture of the top-heavy conjecture, what it says. Okay, so I should be clear that this gets much more, these posets become a lot more complicated. If you can start allowing hyperplanes to sit on top of each other. You know, they don't have to be generic. And then this intersection lattice is sort of a mess. Okay, I've just given you the very sort of nicest examples. Okay. So if some people sort of know about Coxeter groups, I would like to tell you sort of about what you can see the top-heavy conjecture inside the Bruja poset as well. So this is top-heaviness elsewhere.
I have a minor question.
Yes.
So here the assumption is that the arrangement is central and essential.
Yes.
Okay, thank you.
Mm-hmm. Yeah, so that's this intersection of the hyperplanes being the origin, correct. Mm-hmm. Okay, so let's take W to be a crystallographic Coxeter group. So meaning this is one that comes from a Dynkin diagram. So I'm going to write Fi superscript W to be the number of elements. This is if you've seen it. It's not important for my talk. I just want to, if you've seen kind of Bruja posets and Coxeter groups before, I want to draw an analogy. So I want to take the number of elements of length I. So this Bruja poset is a graded poset by the length of the words. Okay, so I can look at all the elements in the Bruja poset of length I below some certain word that I pick. That's what FIW means. And of course, this Bruja poset, it's symmetric vertically, because so it doesn't, if you look at the whole poset, it satisfies the top-heavy conjecture trivially. It sort of looks more like this poset It's very symmetric because you can multiply by the longest element of the Weil group or the Coxeter group and flip the whole poset. Okay. So that's why I don't want to look at the whole poset. Instead, I want to look at sort of the part of the poset that's below a particular element. So I look at everything below some element. And here you can say something more non-trivial. So this is a version of the top-heavy conjecture. It says if you draw some horizontal line, then it basically what I just wrote says that the top-heavy conjecture is satisfied for intervals below some certain element in the Bruchau order. Okay. So this is for Bruchau orders inside Weil groups where you have some geometry, you have flag varieties and so on. And this is how it's proven. And then there's some work that's unpublished by Melvin and Slofstra that removed the word crystallographic from Coxeter group. So this isn't the case where you don't have geometry. And they use Zergel bimodules to prove this. So some combinatorial stand-in for the cohomology of a flag variety. So yeah, modules over the equivariant cohomology of the flag variety. Okay, anyway, so this is just, if you've seen this before, good. If not, now I'm going to continue the story about hyperplane arrangements. Okay, so I've explained to you the first problem about the top-heavy conjecture. So now I want to explain to you how I associate to a hyperplane arrangement some Kazhdan-Lusztig polynomials. So some kind of polynomial. Okay, so let's do that.
What is that in the definition? This FIW. Can you?
Sorry, I can't. I can't
so
hear
this FIW. So it's the number of elements of length I. What is that? Length I below.
Yeah, length I below the word W. So you take your Bruchau poset, you pick some word, any one you want,
Yes.
and you look at the poset below it.
Yeah.
Yeah. Mm-hmm.
Okay. Thank you so much. Thank you.
Yep. No problem. Okay. So before I tell you what a Kazhdan-Lusztig polynomial is, I have to give you a definition of some preliminary polynomial that I need to define the Kazhdan-Lusztig polynomials. So V is a vector space, but not over C anymore, or R. I'm going to take it over a finite field with T elements. Okay, and I'm using T just because I want my variable to be T because it's what I'm used to. People usually write Q. So the characteristic polynomial, this has probably come up in other talks, characteristic polynomial of a matroid, and then this Adiprasito, He, and Katz work saying that the absolute values of that sequence of coefficients is log concave and so on. So I'm talking about the same characteristic polynomial. So the characteristic polynomial of a hyperplane arrangement, here's a heuristic definition. That's why I wrote a definition in quotes. So there's a definition that makes sense purely in terms of this poset that I've been writing down, but it's sort of not so easy to remember and not so intuitive to me. So this one makes more sense to me, but you have to define it over a finite field. So what I do is I look at the complement of my hyperplane arrangement inside of my vector space and I count how many points I have. Okay, so let me show you what this is in these examples. Or at least let's do one example. So how about this one? So let's compute the characteristic polynomial here. Okay, so I want to look inside this vector space. I want to take out these three hyperplanes and count how many points I have, but I'm working over a finite field with T elements. Okay, so this is a two-dimensional vector space, and over a finite field with T elements, there are T squared many points. And then now I remove these three lines. So I have minus 3T, but I'm only trying to look at the complement. And if I remove these three lines, I've removed the origin too many times. Okay, so I removed the origin 3 times, so I have to sort of add it back in twice. Okay, and so this is the characteristic polynomial. And you could do a similar computation here. It's just a little bit longer. I won't write it down, but it's this inclusion-exclusion type thing. Okay. And like I said, you can define this in terms of these posets with some definition that always works for all matroids, but it's in terms of the Mobius function, and it's a little bit more unintuitive. Okay, so now that I have this characteristic polynomial, I want to tell you that so these posets that come from hyperplane arrangements have a property that the posets that come from Coxeter groups and vowel groups don't have. Okay, so anytime that I pick an element inside of one of these posets, so this one's bigger, let's do it here. So if I take an element, whatever element I like, I can look at the poset that is above this element. Okay, so like this subposet here. Okay, so I take all of the elements above along with their edges. Or I could look at the subposet of everything below that element. And the nice property is that there exist hyperplane arrangements whose lattice of flats is those posets. Okay, so you can cook up hyperplane arrangements. So when you write down all the intersections of the hyperplanes, you get these upper and lower intervals. Okay, so this is sort of not true for Bruja poset. So if I put these two things together, I can like pick an element and pick another element, and I can look at the interval in between. And I'm saying that there's always a hyperplane arrangement that gives me its poset is any interval. Okay, this is not true for Coxeter groups. It's not true that you can take a Coxeter group and then pick an interval inside of it, and you can find another Coxeter group whose Bruja poset is that interval. Okay, so let me sort of just write down so you can remember what I said. So all I'm saying is that if for every element inside of my lattice, so pick any element inside your poset, you have posets where you take the lower interval below everything below that element. I'm going to write this poset like this, L of A super F, sort of to mean that I'm taking everything below like this. And then I also can do the other thing where I pick an element and I look at everything above. And I'm going to write this poset like this. Okay. And these are gotten by either quotienting all the hyperplanes by the flat that you pick or intersecting all the hyperplanes with the flat that you pick. Okay. This is how you get these hyperplane arrangements. But just know I won't need the construction. Just know that I can pick any element and look at the upper and lower intervals. So here's the definition of Kazhdan-Lusztig polynomial. And this was given by Elias, Proudfoot, and Wakefield in 2016. So I'm going to use these characteristic polynomials that I defined a minute ago. So it says for every hyperplane arrangement, A, there exists a unique way to give a polynomial to that hyperplane arrangement such that this polynomial has integer coefficients and it satisfies the following properties. So this polynomial is going to be called the Kazhdan-Lusztig polynomial. Of the hyperplane arrangement A. So it should satisfy the following properties. If the dimension of the vector space that my hyperplanes are sitting inside is 0, then I make that polynomial 1. Polynomial has to be 1. Okay, so in the non-trivial case where the dimension of the vector space is positive, there's a degree bound. So the degree of the polynomial has to be strictly less than 1/2 the dimension of the vector space. And here's sort of the most important one. It's the recursion that defines the polynomials. For every hyperplane arrangement A, I have the following recursion. So t to the dimension of the vector space V times this Kazhdan-Lusztig polynomial evaluated at t to the -1 is equal to this sum. I sum over all the elements inside of this poset, and I take the characteristic polynomial for the lower interval at f times the Kazhdan-Lusztig polynomial for the upper interval at f, and I sum over all f. Okay, so this is some recursion. If you've seen Kazhdan-Lusztig polynomials in Coxeter groups, it's sort of the same recursion, except you're sort of in a different setting. You have a Bruja poset And instead of the characteristic polynomial, you have something called the R polynomial. So your post set is different, and your sort of intermediate, your sort of building block polynomial is different. Okay, but it's once you change these two things, it's the same recursion. Okay, so one thing I want to point out about this recursion is that you might be nervous when you look at this and say that you can't solve this because why did I write L? I meant F. Okay, so you might be worried that you can't solve this because at the bottom of all these post sets here, you have the vector space V. Okay, and if I look at the interval above V, that's the whole post set. Okay, so in this recursion, if I'm going to have a summand here for F equals V for the bottom element. Okay, and then here, if F equals V, I get the whole post set. So this is the Kazhdan-Lusztig polynomial P of A. So this is the whole Kazhdan-Lusztig polynomial, this one. And here I have the same polynomial here, but evaluated at t to the minus 1. So you might worry that I have the polynomial on both sides. How can I solve? Okay, but this comes in to save you that there's this degree bound. Okay, this degree bound is allowing you to solve this equation. Okay. Okay.
Any questions?
And now I would like to go here and just tell you what they are in these two examples that I've shown before.
Can I ask?
Yeah, please.
So here, are you assuming that the hyperplane arrangement lives in its proper? I mean, what is the term? Essential or something? I mean, you can have lines in R3, for example, right? They also form a hyperplane arrangement, or do you?
No, I mean I want them to be hyperplanes, so they should be codimension 1.
Always codimension 1.
Yeah. For me, hyperplane means codimension 1.
Okay. Thanks.
Yeah, I mean, right. I mean, if you take some lines that all sit inside a plane, say they all sit inside of a plane inside of R3, then I would just do the computation one step down. But yeah, I always assume that everything is codimension 1. All my hyperplanes are codimension.
But the coefficients, aren't you assuming they're integral so that you can specialize to finite field, something like that, to each finite field? You're assuming the coefficients are integer, right?
I am, yeah.
Which is the generic. Okay.
Yeah, I'm assuming that they're integers.
The hyperplane arrangement.
He's asking about the defining equations of the hyperplanes. They also have to have integer coefficients.
Yeah, okay, so I don't think it matters. So I mean, you can make this definition for arbitrary matroids. Okay, so you can, right. So I think if a hyperplanar, forgot how realizability works. So,
Probably can,
Yeah, go ahead.
Yeah, I mean, you can approximate it without actually probably spoiling the structure of the matroid by keeping the structure of the matroid intact.
Yeah, I think you can shift everything around slightly.
Yes.
So and then it won't be a problem.
Yeah. Okay.
I mean, yeah, these notions of realizability are not so sensitive to this kind of stuff.
Yes.
And this definition is going to make sense for arbitrary matroids. So I just give you a post set. This is called a geometric lattice. So meaning the post sets that come from matroids that are equivalent to the definition of matroid. And so if I have a post set M, so just call it a matroid M. So one of these geometric lattices, it's some post set satisfying axioms, and these are more general than hyperplane arrangements. Then you can make the same exact definition. And here, instead of defining this characteristic polynomial in terms of counting points or a finite field, I don't worry about that anymore. You can define this in terms of this Mobius function on this post set. So all of this goes away, sort of all of this worry. Yeah.
Okay. Yeah. Thank you.
Yeah. So then you worry this worry about realizability is not a worry here because this definition makes sense for all matroids, regardless of whether they're realizable. Oh, they can be realizable over vector spaces over like no fields at all, like for no fields, right?
Yes.
So they can be not realizable at all. Yeah.
Thank you.
Yeah, no problem. Okay, so now let me tell you a theorem by the same people. So this is in the same paper that they were defined. So for every hyperplane arrangement, the Kazan-Lusztig polynomial associated to it, does it? Sorry, any other
I
question?
have a minor question. This
Yeah.
Kazan-Lusztig polynomial that is defined, does it have a combinatorial interpretation in terms of the metroid?
Yes. Yeah, I'll get to this. Ask me
Oh.
a question. Ask me the same question again at the end if you still have, if you want sort of a, if you're not satisfied.
Okay, okay.
Yeah, yeah.
Okay.
So I'll get to it. It has a hard interpretation, but it does have one. Yeah. Okay. So this polynomial has not just integer coefficients, but the non-negative coefficients. Okay. So this was this non-negativity. This is the second problem that I talked about. Okay. So I gave you two problems. I have top heaviness and non-negativity of these polynomials. Okay. So I would like to now hopefully give some intuition about sort of what are these problems? Where are they coming from? How do you solve them? So I want to tell you about the proofs of this top heaviness and non-negativity of Kazan-Lusztig polynomials for hyperplane arrangements. They both make sense for arbitrary matroids, but let me tell you about the restricted case where I'm considering hyperplane arrangements. Okay, so now I'm going to use some algebraic geometry. So first, let's focus on the top-heavy conjecture. Okay, so I'm looking at the shape of these posets. So there's a vector space V that all of my hyperplanes sit inside. And now I can consider the quotient map where I quotient by any of these hyperplanes, H. And then I can look at the sum of all of these quotient maps over every hyperplane in the arrangement. And remember, I assumed that I had a central and essential arrangement. So I assume this. So that means that this sum of quotient maps is going to be an injection because of this condition. Now, these hyperplanes are codimension 1. So that means I have some vector space in a codimension 1 vector space. So when I quotient, I have a one-dimensional vector space. So I have a big sum of one-dimensional vector spaces, okay, affine lines. And what I'm going to do is I'm going to compactify this big sum, not by having it sit inside Pn, where n is the number of hyperplanes, but having it sit inside of a product of P1s, okay? So I'm going to add a point at infinity for every hyperplane in the arrangement, okay? So here's a definition of the main sort of variety, the main geometric thing involved. So this is the Schubert variety. This is now called the Schubert variety of a hyperplane arrangement. So what I do is I look at the closure of this vector space inside of this product of P1s. So I want to draw some pictures to give you an idea of what this looks like. And it's called Schubert variety again because it's sort of not a Schubert variety from flag varieties in this classical Kazan-Lusztig setup, but it plays a similar role in this theory. Okay. And you'll see some of the properties that it has. That if you know the classical story, you'll see that it plays a similar role. Okay, so in example 1, this is just to show you we had these three lines inside of this vector space. So let me show you what the Schubert variety is in this case. Okay, so in a neighborhood of the origin, it looks like the vector space V that you started with. And on the other side of the world, right, we're adding a point at infinity for each, we're adding a point at infinity for each hyperplane. So sort of at the other side of the world, there's an affine neighborhood of the most, this infinity, 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 this sort of most far away point. And here, it looks like an affine cone. So here is the point infinity, infinity, infinity. Okay? So first off, it's a singular variety. So this variety Y is a singular projective variety. Okay. And its nicest property is that it has a stratification by affine spaces. So there's a way of breaking it up into affine spaces, just like Schubert varieties in the classical case has. And these affine spaces, you can really write down what they are. So first, stratification by affine spaces means that it's a disjoint union of Y sub F that are all affine spaces. And these affine spaces are parameterized by the elements of the poset. Okay, so there's one for every element of the poset. And let me tell you now what these strata are. So they're easy to say what they are. So I take all the points P inside of my, so I'm going to write Y now instead of Y sub A, because I'm only ever going to have one Schubert variety, one hyperplane arrangement in mind. Okay, so I'll drop this A. So the coordinates corresponding to hyperplanes H should be not infinity if and only if the flat labeling this stratum is not contained in the hyperplane, or is contained in the hyperplane. Okay, so let's go through an example. I'll show you sort of the two most extreme cases. So let's say I take the bottom element of the poset. This is the vector space phi, and I want to see the stratum corresponding to this, the affine space. Okay, so I've picked F equal to V, and I look at this condition here. Is V contained inside of any hyperplane? No. Okay, so it's contained in none of the hyperplanes. So this is an if and only if condition. So that means that all of the coordinates should be equal to infinity. So this is just a point. This is this point in this example. In general, you just have, the infinity, 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 infinity point. Okay. So what about at the other extreme? So at the top of the poset, I have the origin, right? So I'm taking F to be the origin. The origin is contained inside of every hyperplane. So that means all of the coordinates should be not equal to infinity. And when all of the coordinates are not equal to infinity, that means you're in this affine neighborhood. Okay, so this is isomorphic to the vector space V that I started with. Okay, so people often like to see stratifications in terms of group actions, like they are the orbits under some group action. You can also see it this way. Okay, so let me just say this in a word. So let's look back at the construction here of the Schubert variety. I had this vector space V. So a vector space, I mean, it has one operation, it has this addition, and it acts on itself by translation. Okay, so any vector space acts on itself by translation. So the vector space acts on its closure. Okay, this action extends to the closure. So the vector space acts on the Schubert variety by translation. So you can look at this action and you can break it up into orbits. And these are exactly the orbits under this action. So in particular, this Y sub F stratum is the V orbit with stabilizer F. Okay. And then you can see what the dimension of this affine, you can see what the dimension of this stratum is. It's the dimension of V minus the dimension of F. Okay. Good. So it's the codimension of F. So it's the rank of F. Okay, so now I want to tell you about two properties of having a stratification by affine spaces. So what I'm about to say has nothing to do with hyperplane arrangements or matroids or classical Clausian-Lustig polynomials. It's just anytime you have a variety that's stratified by affine spaces, you have the following two things. Okay. So I have a poset that labels the strata. So first, the odd degree cohomology vanishes, and the even degree cohomology, the dimension of it, is given by the number of elements at that particular level in the poset. And number two, I already mentioned this paper, Björner and Eckerdal, when I was talking about this top heaviness inside the Bruja poset. In the same paper, they proved that the cohomology of your variety injects inside the intersection cohomology of your variety. So if you haven't seen intersection cohomology before, I'll just say the tagline, right? So when you have cohomology of a smooth projective variety, you have all these nice things you've seen in talks before, like this Kähler package, Poincare duality, Hard-Lefschetz theorem, Hodge-Riemann bilinear relations, all of these things. So now if you take a variety that is not smooth anymore, it's singular. If you have a singular projective variety, you have to use intersection cohomology to have those things be true. Okay, so intersection cohomology satisfies all the nice properties of usual singular cohomology when you have a non-smooth space that's still projective. Okay. So now let me sort of give you the proof of the top-heavy conjecture. We've sort of built up everything we need. So looking at this property here, if I take this and I look at what the top-heavy conjecture says, then I can restate this in terms of some dimension is less than some dimension. Okay? So let me rewrite this. So remember the top-heavy conjecture said that the number of elements in my poset at rank K should be less than or equal to the number of elements in my poset in the complementary rank. Okay, this is what I want to prove. So to prove this, using this property 1, I need to show some dimension is less than some other dimension. I need to show that the dimension of this space is less than or equal to the dimension of this space. So basically I need an injection. If there's an injection between these two vector spaces, then I know that the dimension of the bottom one's less than the dimension of the top one. Okay, so I'll try to produce an injection. Okay, so what I do is I take some particular element L inside the degree 2 part that's called an ample class in algebraic geometry. But for matroids, this has a very simple description. And then remember, I have this K should be less than or equal to 1/2 the dimension of the vector space. This is my horizontal line through the poset from the beginning. Then I have the following diagram. Okay, so part 2 here says that cohomology should inject inside intersection cohomology. And this is actually a graded map. So it sends like degree 2K to degree 2K here. And same thing here. So this is the Björner-Eckerdal injections from above. Okay, and now this, I can take an element in the degree 2K part, I can send it across, and I can multiply by it some number of times to go here. Okay, so let me write down what I'm saying. So I can multiply by this element in degree 2 enough times. This is a multiplication map. I multiply by enough times to get in complementary degree. So it's in degree 2. So I keep adding 2 to this degree. This is how many times I have to add it, and I end up here. So it's a multiplication map where I iterate this multiplication many times. And then I said that sort of everything you'd like to be true is true about intersection cohomology for singular projective varieties. And this Y is singular. And the Hard-Lefschetz theorem says that this should be an isomorphism. So I'm just appealing to some big theorem in algebraic geometry. It says that this is an isomorphism. Okay, but I have an injection, I have an isomorphism. I can restrict this multiplication. Instead of sending it through this injection, I can restrict this multiplication to here. And this is a commutative diagram. Okay, so I have an injection, I have an isomorphism, I have another injection, and this diagram commutes. So just formally, if you have two injections and an isomorphism and a commutative diagram, that forces this map to also be an injection. Okay, and that's it. So this is what Junhe and Bozong Wang did. So this is the top-heavy conjecture for hyperplane arrangements. And I think it's a beautiful proof. It's sort of like build some variety and then uses some deep theorems from algebraic geometry to prove this purely combinatorial thing, right? It's like some number is smaller than some other number. Okay. So now there was this other problem, which I went through some process of showing you how to associate this Kazhdan-Lusztig polynomial to a hyperplane arrangement. This was some polynomial with integer coefficients, and it satisfied some properties. And the second problem was that this polynomial should have non-negative coefficients. Non-negative, they're integers, but they should also be non-negative. And here's the theorem in the same paper that these polynomials were defined. So I take, so this, somebody asked me like, what interpretation does these Kazhdan-Lusztig polynomials have? Okay, and here's some kind of answer. It's not a combinatorial interpretation, it's sort of a topological interpretation. So it's a Poincare polynomial. So its coefficients are dimensions of something. So I take this intersection cohomology of this Schubert variety associated to this hyperplane arrangement A. And its coefficients are dimensions of this, except there's one slight technicality. I have to take the stalk at the most singular point. Okay, but whatever this means, it doesn't matter. All I'm saying is that the coefficients are dimensions. They have some interpretation as dimensions, so they're non-negative numbers. Okay, so this implies that the coefficients are non-negative integers. Okay. So I've given you and the way that you prove this is sort of like Lefschetz fixed point formulas and traces and all kinds of L-adic intersection cohomology. It's sort of a standard argument, but it uses a lot of machinery. Okay, so I've now told you about two problems, and I told you about their solutions when you have hyperplane arrangements, and it uses lots of topology. Okay. I would like to now quickly just, so in case you've seen the classical story, so the third part of my talk was to tell you that, well, I've been describing this sort of some kind of theory for matroids, and there's a classical Kazhdan-Lusztig theory for sort of Coxeter groups and Weil groups, and it shows up in the representation theory of Lie algebras and all of this kind of stuff. So if you've seen this stuff before, you can listen now. If you haven't seen it before, it won't take more than 3 minutes or 4 minutes. Okay, so it's just for the people who've seen it. So in the classical story, you have a Weil group, okay? And this, in our setting, corresponds to the hyperplane arrangement that you start with. But everything sort of works in a more general setting. So when you have a Weil group, you have flag varieties, you have all this geometry. And we saw when we have a hyperplane arrangement, we can build a Schubert variety. Okay, and similarly, when you have a Weil group, you can build a Schubert variety. Okay, in both settings, you have a poset. So you have the Bruja poset on this side. You have this lattice of flats on this side. You have a characteristic polynomial that I described to you. You have an R polynomial, which is your building block on this side. Okay, in the more general setting, for an arbitrary Coxeter group or an arbitrary matroid, you don't have this Schubert variety anymore. You don't have geometry. So this whole, this line in the table is cut out. Okay. But you still have all of the other things. You have a poset, you have this polynomial. So these two problems make sense. You can talk about the shape of the poset, this top-heavy conjecture, and you can talk about these Kazhdan-Lusztig polynomials having non-negative coefficients. But you don't have the main ingredients to solve these problems don't exist. You don't have geometry anymore. You have no Schubert variety. You can't define this Y. Okay, and so I showed you. So these classical Kajan-Lusztig polynomials were proved when you don't have geometry. In the arbitrary Coxeter group case, they were proved to have non-negative coefficients by Elias and Williamson in 2014. And these polynomials were defined in 79 and 80, so a long time after. And then we proved the matroid case when you don't have geometry. So all of these things have been comparisons. Let me talk about something that's different. So the polynomials in the classical Kajan-Lusztig case, so I'm just talking about this line here. So the polynomials in the classical Kajan-Lusztig polynomial case, they're kind of boring. So they carry lots of great information, but as polynomials, they're not interesting polynomials. So basically in the classical case, there's this theorem by Polo in 99 that says Kajan-Lusztig polynomials are common. Explicitly, it says that every polynomial with non-negative coefficients and constant term 1 is a Kajan-Lusztig polynomial already for the symmetric group. So most polynomials are Kajan-Lusztig polynomials. In the matroid case, the Kajan-Lusztig polynomials are very special polynomials. It's conjectured that the polynomials should have real roots, which is sort of a very special condition. I mean, most polynomials don't have all of their roots being real. Okay, so that's one difference. Okay, so I would like to spend the last sort of 5 to 7 minutes or so of my talk giving a sort of glimpse at how do we prove this top-heavy conjecture and this non-negativity of Kajan-Lusztig polynomials when we don't have geometry. Okay. So this is sort of like this part here. Okay. So now in matroid language, hyperplane arrangement means realizable or representable matroid. So if a matroid comes from a hyperplane arrangement, it's called realizable or representable, but many matroids don't come from hyperplane arrangements. Okay. So, but all of the problems make sense. Like I said, matroids have a lattice of flats, they have a post set, and they have a rank function. So all of the two problems make sense. I don't think that this was stated before in a previous talk, so I'll state it. So most matroids don't come from hyperplane arrangements, and I want to explain in a precise sense. Most matroids are not representable. So you can say this precisely. So let Rn be the number of realizable matroids or representable matroids with n elements. So meaning having n hyperplanes. Oops. And I'm gonna let Mn be the number of matroids with n elements. Okay, so all matroids. Then there's a theorem due to Nelson in 2018 that says that if I look at the ratio of the number of realizable matroids with n elements to the number of all matroids with n elements, then as I let the number of elements go to infinity, this ratio tends to 0. Okay, so this is a precise sense that most matroids are not realizable. Okay. So how do we prove these two statements when we don't have geometry? Well, if we look back at the main sort of diagram, we needed cohomology of some variety and intersection cohomology of some variety, but this variety doesn't exist. So we need some combinatorial stand-in for these two objects. So we need combinatorial stand-ins for the cohomology of a Schubert variety and the intersection cohomology of a Schubert variety. So let's talk about the first guy here, the cohomology of the Schubert variety. There's sort of a well-known object in this area called the graded Möbius algebra. And it's it's pretty old. It's before all of this. And as a vector space, as a graded vector space, so I'm going to denote it the cohomology of a matroid like this. So as a graded vector space, it has a generator y sub f for every element of my post set. Now I'm writing L of m instead of L of a just because I have a post set associated to an arbitrary matroid. And I stick these y sub f's in the degree the rank of f. So that's what it is as a graded vector space. And I said it's an algebra, so I need to tell you what the multiplication is. And the multiplication is very simple. So if I multiply two of these generators, it's either 0 or it's another generator associated to the, I think that's called join. I always confuse what is join and what is meet. But it's the least upper bound of f and g inside the post set. Okay. So it's this if the rank of f plus the rank of g is equal to the rank of the join. And the other thing that can happen is that the rank of the sum is greater than the rank of the join. And in that case, it's 0. So just one comment. I mean, this is supposed to be the cohomology of the Schubert variety. So this is another very different sort of a contrast to the classical setting, right? So people study Schubert calculus in the classical setting, and this is like complicated. You know, it's Schubert calculus is a complicated thing. Here, so this is like multiplying, you know, Schubert classes, and here it's very easy. You multiply the Schubert class and you just get another class. Okay, so the Schubert calculus here is very easy compared to the classical case. Okay. So can I ask somebody how much time do I have? Is like 3 or 4 minutes okay?
Absolutely, yeah.
Okay. So here's a theorem in the same paper that this top-heavy conjecture was proved for realizable matroids. So Junhe and Botong Wang proved that this graded Mobius algebra here is, I mean, it's the right thing when your matroid is realizable. So it is, and I have to do a degree doubling. So it is the cohomology of the Schubert variety when your hyperplane arrangement realizes the matroid. So if the matroid is realizable, then it is the right thing. But you can define it for arbitrary matroids. So I've described to you what the combinatorial stand-in for all matroids for this is, and now you have to come up with what the combinatorial stand-in for this is. I gave you sort of a generators and relations definition here. It's really hard. At least we don't know how to come up with generators and relations for this because this is not a ring. It's a module. It's a module over this. So I don't know how to present it. So here's what we do instead. We present something combinatorially that's bigger. So we have this Schubert variety. So now I'm back in the geometric case and I'm trying to get motivation for how do I define this thing combinatorially. So I have this Schubert variety Y. It's singular, it's not smooth, but it has some explicit resolution where I have a sequence of blowups. And I can tell you explicitly what the sequence of blowups is. So I have some resolution Y tilde that's very canonical. And we can describe the cohomology of this. And I'll state it because I think it's come up in Alex Fink's talk. So this thing is called the augmented Chow ring of a matroid. And in the first part of this talk at the very beginning, I said that there were 2 papers. This is the smaller paper. We defined this augmented Chow ring. And we proved that it satisfies this Poincare duality, Hard-Lefschetz, and Hodge-Riemann. But for us, it turns out to be the cohomology of this resolution when you have a realizable matroid. So you can define it in general, this has a definition purely in terms of the matroid, and it is the cohomology of this when you have a realizable matroid. So we sort of know the cohomology of the Schubert variety and its resolution, and we can use these two to understand the intersection cohomology combinatorially. So the strategy, this is sort of the last thing I'll say. I'll write down the strategy and that's all. So geometrically, we have the following situation. So I'm always trying to be inspired by geometry. So I have this Björner-Ekadal inclusion of cohomology inside intersection cohomology, and intersection cohomology sits inside the cohomology of the Schubert variety. And combinatorially, we know this is the graded Mobius algebra, and this is the augmented Chow-ring of the matroid. Okay, so what we do is we first decompose this guy as a module over this. So H of M acts on CH of M, and we decompose it into indecomposables. And then we pick a nice sum n, sort of the biggest sum n in some sense, and this is the intersection cohomology. Okay, so we decompose the augmented Chow-ring as a module over the graded Mobius algebra. Now this all makes sense combinatorially. We find a nice sum n. For time constraints, I can't say too much about what this is. It's the biggest sum n. It's the unique sum n that contains the 0 degree and the top degree, both of which are one-dimensional. And then you have to prove this Björner-Ekadal type inclusion. And then now, if you look back at this commutative diagram that I used to prove top heaviness, you needed hard Lefschetz for intersection cohomology. So you have to formulate what does hard Lefschetz mean in this combinatorial setting, and you have to prove it. So you have to find an ample class inside here that you multiply enough times by to get a complementary degree, and you get an isomorphism. And then you run the same argument. Using this commutative diagram. And this implies the top-heavy conjecture for all matroids. So this is what we did. And what about the non-negativity? So I need to give you an interpretation of the Kazhdan-Lusztig polynomial of a matroid. So it's the Poincare polynomial of this intersection cohomology of a matroid. But remember, we had to take this stock at the most singular point. Okay, so the way that you handle this is you tensor over the cohomology of the matroid, so the graded Mobius algebra with Q. So you quotient by the action of the generators, the yi's in H of M. So in any case, it doesn't matter. It's a Poincare polynomial, so its coefficients are dimensions of now some module. But it's dimensions, so for all matroids, we have that the coefficients are non-negative. Okay, so I'll stop there. Thank you.
Let's thank Jacob for a nice talk. Questions, comments? Yeah.
Hi, Jacob. Nice talk. Can
Hi,
you go
thanks.
back to that table where you were comparing
Yes.
the two things? So I'm a bit confused by the results on the Kazhdan-Lusztig polynomials because some matroids correspond to Coxeter groups, right?
So I guess you're.
So I'm
so,
confused
okay,
on the one
Mhm.
side. So isn't Pm of T the Kazhdan-Lusztig polynomial for certain class of hyperplane arrangements?
No, okay. So I think I understand your question. Let me try to restate it and tell me if this is what you're thinking. So, okay, so I can take some Weyl group, okay, and
Yeah.
or
And
Coxeter group. If
for
say
example, I have
take-
the type A arrangement, right?
Yeah, then I have the type, like the Coxeter arrangement, the type A Coxeter arrangement,
Sure.
right?
Yeah.
And for that, so okay, so just with the symmetric group, I can build a Kajan-Lusztig polynomial in the left-hand sense, right?
Yes. Yes.
And then in the right-hand sense, I can take the Coxeter arrangement. I can build this kind of Kajan-Lusztig polynomial.
Yes.
And I'm claiming these are not the same.
I see.
Yeah. So they are analogous theories, but there's very little overlap. Yeah.
So even for the same object, they define different polynomials.
They define different polynomials. Yeah. Because I mean the poset is different. So there's some nice there's some nice work by Richard Stanley from maybe the 80s or 90s. So he defined some general setup where if you take some poset satisfying some not very restrictive properties,
Yeah.
and you define a something like a rank function on this poset. So
Yes.
then you need something he calls a p-kernel, which is some generalization of this line here. So both an R polynomial and a characteristic polynomial are both examples of p-kernels.
Uh-huh.
So he abstracts what it means to be an R polynomial or characteristic polynomial.
I see.
So if in that setting he shows you some general way to output a Kajan-Lusztig polynomial, and it gives you this Kajan-Lusztig polynomial and this Kajan-Lusztig polynomial. If in this case you take the Bruja poset with R polynomials, in this case you take lattice of flats with characteristic polynomial. So I'm
Okay.
saying they're both special cases of something more general,
Uh-huh.
but they output it's sort of different input into this general framework.
And can you, so can you relate the two polynomials in some way?
Yeah, I don't know how, and I find it seems complicated, or I mean the thing that throws me off is that is this line, like the polynomials are very different.
Yeah.
In this case, almost every polynomial is a Kajan-Lusztig polynomial. In this case, they're sort of very special. They're all row rooted.
No, but okay, but those are, yeah, that's for all matroids, but at least,
Okay, yeah, I
yeah,
see.
in this case, maybe.
Yeah, I don't know. I haven't thought about this in the.
So the conjecture for the real rootedness conjecture for Coxeter groups must be proven, right? Or for, type A arrangement. I mean, Coxeter arrangements must be proven.
Braid, so this is braid arrangements. I think this is not known.
Oh, even this is
Yeah.
not known.
So it's known for some families, like graphic matroids associated to fans, wheels, and whirls. It's known for a large class of uniform matroids, but then the authors had to use a computer, and it's up to some
Check
rank and
cases.
some number of elements.
Yeah.
But I think for braid matroids, this is not known.
Oh, I see. Okay.
Yeah.
Thanks.
Other questions or comments? AV team, can you please allow the online participants to unmute themselves? If there are any questions online, please unmute yourself or type the question in the chat box. While we're waiting, I have a question.
Yeah.
So you call this Hodge theory. To what extent, can one develop all the analogous structures that one has in Hodge theory here? For example, is there a Hodge filtration kind of structure, or I mean, traditionally Hodge theory has to do with finding some metric that some form that minimizes some action,
Sure.
some energy. But
Yes.
So that's the old, and then you can of course algebraically package it as some filtration. How much of that can you push through in this context?
Yeah, I don't know the answer to this. I mean, in terms of there's a notion of purity for intersection cohomology, and all this intersection cohomology is pure. So maybe this is a different filtration. This is sort of the weight filtration in intersection cohomology. I'm saying there's nothing to see here.
Uh-huh.
It's all like PP.
Right.
Yeah, but yeah, I don't know the answer to your question. Yeah.
Yeah, I guess that ties into like the thing you just said ties into a different question, which is related, which is so if I understand correctly, the matroid things you're talking about here, the cohomology groups are analogs of cohomology groups of Schubert varieties, right?
Yep.
But is there a more general class of spaces, you know, analogous to algebraic varieties or something that one can make sense of in some combinatorial context, generalizing matroids or something? I don't know.
Yeah. So this is a great question. I'll answer something. I mean, maybe slightly different, which I think maybe it's an answer. So if I look again at this table, right? So here there are Schubert varieties, the classical ones. Here there are these hyperplane arrangement Schubert varieties, and then there's a third table which has to do with toric varieties. So in terms of toric varieties, you can sort of write the same thing here, where your post set is like the face lattice of some polytope. And then there's you have a toric variety that's rational in some sense, and then sometimes it's a bad toric variety. It's not rational, but in any case, you have this thing called a toric G polynomial, which is like playing the role of this Kazan-Lusztig polynomial. It's just called toric G polynomial because different people were working on it. So I guess I'm saying that there's a third column that has to do with toric varieties that you could write down sort of all of the analogous things.
Right.
But it's not. Yeah, I mean, I think like a general framework of trying to come up with a combinatorial analog of geometric things is not known. This is probably a really hard question. Like one would like to take this Kazan-Lusztig, like the Stanley framework that I was just talking about. And you know, anytime you have some general poset and some kind of thing that's like an OR polynomial or like a characteristic polynomial, this P kernel, and it you know, Stanley tells you how to output a Kazan-Lusztig polynomial, and the hope would be like, in this case, you can develop some combinatorial machinery to play the rest of the game. But I think the problem is that Stanley's framework, it's very general. So the polynomials that it outputs will not automatically have non-negative coefficients. So they won't sort of automatically be something geometric. Right. So a nice question would be like, in what settings do you get non-negative coefficients? But I think this is quite hard. I should mention there's a survey by Nick Proudfoot called The Algebraic Geometry of Kazan-Lusztig Stanley Polynomials. And he gets into this a bit, where he takes this general Stanley framework and he proves in some level of generality when you have a geometric setup and when you don't, and stuff like this. But there's still a lot. Yeah, the general question is quite hard about coming up with combinatorial sort of objects that model the geometric thing that's output by this Kazan-Lusztig framework.
I see. Thanks. That's really helpful.
Yeah. It's a good question, but I think it's a great question, and it would be great, and I think it needs to be answered, but it's quite hard. I think it's a big question. Yeah.
Right. Yeah, I'm not an expert on this stuff, but I mean, there's this notion of the geometry over F1, the field with one element.
Yes.
And I was wondering if like all this somehow can be, is there some relation? Can it be understood in that framework?
I think, I don't know anything about that, but yeah, I think some people have thought about some starting bits of this, but yeah, I don't know what the progress is. Yeah.
Other questions or comments? Anyone online? Questions? Yeah.
So when is the polynomial PMT for what matroids? Does it completely factorize any?
Right. So you want to prove real rootedness in this way or something?
Yeah. For what kind of matroids? Any?
I think usually not. I don't know a characterization, but I think it usually doesn't factor.
Okay.
Yeah. yeah, I think that yeah, I think this is sort of the first thing one thinks about when they try to prove rootedness. Just try to factor it, right? But
Yeah.
I think this is not this doesn't happen so often in this case.
Okay. Okay. Thank you. Thank you.
Thank you.
Other questions? If not, let's thank Jacob again for a wonderful talk.
Thank you.